All right, so yesterday we looked at 7.2, okay, how to solve some types of trigonometric equations algebraically. We'll do a little bit of that today. So some of what you see is going to be repeat, and you don't need to rewrite it. Some of it will be some new stuff. Okay, this is a repeat. Okay, we've already talked about this. How do you find the solutions to a trig equation or trig function? First thing you have to do is find all the solutions in one period. Okay, just like we did in the homework last night. And then you find all the solutions by taking into account the period of the function. So for example, if you're working with sine and you had your solutions, you'd put plus in radians 2 pi k on the end of each solution. If you were working with tangent and you had your solution for that period, you'd put plus pi k on the end. Okay, so sine, cosine, secant, cosecant. All those functions have a period of 2 pi. Tangent and cotangent have a period of pi. Okay, we're going to talk about what happens when you take a trig function and raise it to a power, like sine squared, or sine cubed, or sine to the fifth. How does the period change there? Well, it turns out there's a nice pattern to it, so I'll show you what that pattern is. Okay, so just to kind of warm up a little bit, review from yesterday. Sine of x equals 0.8. Find all solutions. Okay, who can tell me how I find one solution? How do I get my first solution? Bless you. Oh, Cody?
Take the sine of 20. Or no. Do the inverse sine.
Yeah, we're going to take the inverse sine of 0.8. Okay, that's going to give us one solution. You don't even need a graphing calculator. Let's do it in radians. Maybe we'll switch throughout the class between radians and degrees just to kind of practice both. But let's do this one in radians. 0.8 inverse sine. I get let's go 2 decimals, 0.93. Okay, and what do I need to put on the end of that? Because that answer can reoccur every period. James? Plus 2 pi k. Okay, so there's one answer. Now I need my second answer. I'm looking for where the sine is a positive value. Okay, we've got an answer in the first quadrant. What other quadrant is sine positive in? 2, 3, or 4? 2. So I'm looking for an answer in quadrant 2. Do you remember what I do with 0.93 to get an answer in quadrant 2? Close. Very, very close. That would be perfect if we were doing something else, but just a little off.
Can you subtract that from pi?
From pi, because we're doing radians. So it's pi minus 0.93. 2.21 is your other answer. And that answer will reoccur every 2 pi k. Just to be kind of formal about it, we should say k is an integer. That's what that means. K is an integer. Okay, any question on that? If you wanted to double check, you could graph sine in y1, graph 0.8 in y2, second calc intersect. You could find both of these that way as well. But you don't need to. Right, so if we have a function and we set it equal to 0, okay, we've done this a lot. You're finding the roots of the equation, or you're finding the zeros. It's also the same thing as saying you're finding your x-intercepts. Okay, so we're going to do that today as well. We're going to set equations equal to 0 and find the roots. Okay, if you have a function that's periodic and you set it equal to 0, well, now you have an equation that's periodic. Right, so if you start off with a periodic function and you take that periodic function and set it equal to 0, you're now finding the roots of a periodic equation. So just kind of small extension of what we know. If I'm solving a periodic equation and I find a root to a periodic equation, what does that mean? If I find a root to a periodic equation, what can you automatically infer from that? About Colby? And the hint is it's a periodic equation. We didn't just find we're not going to be finding a root for an equation. It's a periodic equation. So if you find one root, we are setting a periodic function equal to 0. So if we find one root to that, what does that mean? Well, Darren? Tell me what that means. What does periodic mean? That's the whole key. If you know what the word periodic means, then you know something very important. Yeah? It reoccurs. So if you find one root to a periodic equation, congratulations, you just found infinitely many. Okay? And we write them just like we do a solution to a problem like this. We'll put the plus 2 pi k on it. So we find a root, and that root will reoccur in every period. Now this part, you pretty much already have in your notes. Okay? So you just watch this part. So let's suppose that you have an equation, you set it equal to 0, and it has n roots. Okay? Let's say the first root is x1, and you find another one at x2, another one at x3. Well, to write all your solutions, you write each root that you found on the calculator plus the period times n. 2 pi, or k, if you want to use k or n. It doesn't matter what the variable is. But the idea is you find each solution and put plus the period times n for every solution you have. Okay, so this is exactly what we did right there. Same thing. Okay, any question on that? Okay, what's going to get a little bit tricky to figure out is the period. Because we're going to work with functions that aren't just sine and cosine. We're going to do like cosine cubed, sine squared, and we're going to mix them. So we're going to have to come up with a way to figure out how we find the period of more complicated trig expressions. So if you've got a more complex trig function or expression, what you're going to do is find the period of each individual periodic term. Okay, periodic terms are terms that if you were to graph them, they have patterns that repeat over and over. That is not a periodic term, x squared. X squared doesn't repeat. It's a parabola, it just keeps going. It never comes back down and does the same pattern over and over. Okay, so for our purposes, periodic terms mostly are trig terms. Sine, cosine, tangent, things like that. And then the period of the entire expression is the least common multiple of all the individual periods you found in the first step. Let's say you found something that one term had a period of pi, another one had a period of 2 pi, another one had a period of 3 pi. Right? Each of the individual terms. Well, the period of the entire expression would be the least common multiple of pi, 2 pi, and 3 pi. Anybody think of a number that all three of these divide into nicely? Yeah? 3 pi is too big to go into pi. So your least common multiple has to be bigger, at least bigger or equal to the largest number. It can't be smaller than the largest number. 6 pi, yeah. The period, if this was the period of the first term, second term, and third term, the period of the whole thing would be 6 pi. That's the least common multiple. Think of it as the least common multiple of 1, 2, and 3. 6. And then put a pi on it. Great. So generally, you'll see periods pi, 2 pi. Those numbers come up a lot. So I want to find all solutions to this equation. Okay, first thing I have to do is figure out what the period of it is. And then I can use the calculator to help me find the roots. That's the easy part. But I have to know what to add onto each root. Is it plus 2 pi k? Is it plus pi k? Is it plus 6 pi k? We don't know. We've got to find the periods. Okay, let's start with sine. Okay, just the basic sine function. Who can tell me in radians? What's the period of sine? James? 2 pi. Now, what's the period of cosine? I know we have cosine squared, but who can tell me just what's the period of cosine? There? 2 pi. Well, let's see cosine squared. Let's graph it and see what it looks like. Okay, so when I type it in on the calculator, I have to type it in like that. Cosine squared. Let's hit graph. And that's what we get. How could I find the period of that? Just by looking at the screen. Period is the distance before it repeats itself. So what could I kind of easily do here to measure the distance before it starts to repeat itself on the screen? Thoughts on that? Oh, Brianna? Okay, I could try to change the window until maybe I just have one of these. We'll call these like little mountain things in here. Until I just have one of them. But what about if I just wanted to use that window? So does it look like that graph is repeating at all in that screen? Yeah, it's repeating a bunch of times. If let's say I put a point right here. Could you give me another point that looks like it's a repeat of that point? Where would it, can you kind of describe where it would be? The second tick mark right on the curve? Yeah. Those 2 points are repeats of each other. So all we have to do is find out what's the distance between those 2 points. How can I do that on the calculator? How could I find out exactly where that point is, and then see how far apart they are? Yeah. Okay, I could try and use the table if they line up nicely. How about, so you could do that, but is there any feature under calculate that would help me? Yeah, calculate the maximum. See where it occurs, not on the y-axis, but on the x-axis. Okay, we're pretty clear we're at 0 here for this one. 0.0000007. All right, so we're basically at 0. And let's see where the next one occurs. So calculate the maximum. I think you can probably already kind of tell where it's going to be roughly. It's at 3.14. So what's the period of this function? What's the distance between 0, well, that peak and that peak? Yeah, pi. Yeah, it's pi. Okay, so now you know the period of cosine squared. It's pi. So now you don't have to go back through and try to figure that out again. 1 is not a periodic term, plus 1. Right, so we found the period of each individual term. What's the least common multiple of pi and 2 pi? There? 2 pi. Okay, the period of this function, the whole thing, is 2 pi. Now what we're going to do is we're going to graph that whole thing. We're going to find all the solutions in one period. So I need to set my window to a width of the period and write down every root that I see. All right, so we can already use some of what we have here. So 2 cosine squared plus sine plus 1. And it's already equal to 0. If it wasn't, I would move something to the other side so it was. That's normally how we do it. Okay, now I'm not looking at a window of my period. Set it from 0 to 2 pi. That should be good. Let's see what we get. Okay, that's what that function looks like. And if you wanted to see it for multiple periods, it looks something like this. Copy of it. Can't quite get them exactly on top without cutting the other one out, but that's what it would look like. Okay, that's the pattern to it. So what we want to be careful of, it looks like there might be at least one root, maybe 2. Okay, I'm going to zoom in right there and see if there's more than one. Let's just zoom in. Okay, and see what we get. It looks like there's only one. Right, so let's do second calc root and write it down. So, or 0 on my calculator. So just make sure you're somewhere well to the left of it. So look between there. And let's go over here. It's about, it was 4.71 before I messed it up. So root is at 4.71. So that's t. And what should I put on the end of that to make sure that I get all the solutions? Andy?
2 pi k.
Right, 2 pi k. So this period's important because not only it helps us find our window, it also helps us to know what do we have to put on the end of the answer, plus 2 pi k. And that's it. There's only one answer. Okay, I might start getting a little lazy, but k is an integer for every problem today. Okay, any question on that? So that's the process of how you go doing this. All right, there's a couple ways you could do this one. I want to try to do it like we did the last one. So if we're going to find a root, Victoria, what does it have to equal?
0.
Has to equal 0. So how would I move 3 cosine x to the other side?
Can you subtract it?
Yeah, just subtracting. Now we're ready to go just like we did last time. Find the period of each periodic term, and then we'll find the LCM. Hey, Jill, what's the period of tangent? Pi. Good. And Casey, what's the period of cosine? 2 pi. So now, Alex, what's the period of that entire expression? 2 pi. Yep. So that's going to help me to set my window, and that's going to help me to put the correct addition onto the end of each answer. Okay, let's graph it. So we've got tan x minus 3 cosine x. Oh, I zoomed in, that's why. Let's, I always like, start with zoom 6. Well, you can type your window in yourself. Let's go from 0 to 2 pi. And y min and max, I don't know, I could reason through how high and low this is going to go. But I'm going to just try negative 8 to 8. And if that's not good enough, I could zoom out a little further. But all I care about is the roots. I'm not trying to find maxes or mins. Okay, so we have at least one root, 2 roots. Okay, so that's what that one looks like. And you can see that it's going to reconnect right here on the other side and start again. Okay, how many roots in the interval 0 to 2 pi? How many do you see? Yep, 2. We've got to find both of them. So second calc, 0. Okay, I'll do the first one, and then I'm just going to look up the answer for the second one. Okay, so we should get one at 2.13. Other answer, right around there, that one is 1.01. You might look at it and say, wait a minute, that's nowhere near the first tick mark. Shouldn't 1 be right around there? Well, my scale isn't going by ones. So these tick marks are not spaced 1 unit apart. That's why 1.01 is way over there. Okay, so I've got that. How about Cole? Anything else I got to do with both those answers?
Plus 2 pi k.
Yep, I'm going to put the plus 2 pi k. Again, k is an integer. Any question on that? Now, some of these equations we can solve algebraically, and we're going to come back to this in Chapter 8. And do some of what we're doing right now with just algebra. In general, if you're going to solve it algebraically, it has to be set up very special. Okay, things have to happen so that you can use the quadratic formula or add factors, because you can't just solve any trig equation by hand, especially when you start putting like cosine squareds and tangent cubes. It gets pretty hard. All right, we'll look at some we can do. Okay, let's start with this. Okay, we already know the period of cosine. That's 2 pi. Now we need the period of sine cubed. It's actually not even sine cubed, it's sine cubed 2x. So the 2 is going to change the period. Anytime you put a number next to the variable inside the argument, that's a horizontal stretch or compression. In this case, compression. And the cube is also going to change the period. Okay, let's see if we can figure out what the period of sine cubed is. Let's look at a picture of that. Sine of x cubed. There's definitely a pattern there. It's not a nice sine wave. It looks a little more kind of jagged. And if we go through and use the same approach I did last time, pick 2 points that look like they're repeating. Maxes and mins are easy because you can find the distance. And if we calculate the distance between those 2 peaks, okay, I can trace it just to kind of give you a quick idea. That one's about negative 4.71. Okay, so remember that. And 1.57. So if you do 1.57 minus negative 4.71, you get a distance between them of 6.28. What number is that really? That's 2 pi. Right? So the distance here is 2 pi. Now, let's throw a 2 in front of the x and see what that does. Okay? It should be a compression by a factor of 2. So it should take this period and shorten it, instead of being 2 pi, down to 1 pi. Okay, and you could do the same thing I just did. If you did a trace, you could find that value, 0.78. Okay, get another one, doesn't matter where. 3.92. But if you take 3.92 and subtract 0.78, you'll get 3.14. Okay, or pi. So the period of this one is pi. Okay, little confusing because you're dealing with this cube and the 2 at the same time. So it kind of makes it a little more complicated. Okay, before we even finish, well, actually on the next page, I'll give you a summary of kind of when it's even or odd, what's our formula we use to find the period? And then you'll see it makes it a lot easier. So we don't have to, you're not going to have to do this guessing and measuring on the screen anymore. Right? So my least common multiple is 2 pi. Now I just need to find each answer. That's it. And then put plus 2 pi k on each one of them. Okay, so we've got 3 sine 2x cubed. It should just cube the 3. That should be fine. If you're concerned, you could put parentheses, but I think that'll be, you know what I'll do? I'll just put a, I don't think that makes a difference. But then they'll do minus 2 cosine x. Set our window from 0 to 2 pi. 0 to 2 pi. And I don't really care about maxes and mins. If I did, maybe I'd have to zoom out a little bit.
Why does the distance between tick marks change?
The distance between tick marks, I think it depends on what you do zoom at. If you do like zoom trig or zoom 6, which is a standard zoom, it changes it for you. I don't really care about the tick marks because I don't use them ever. So if you really wanted to put tick marks every, 1 unit, you could. But, okay, how many roots does it look like I have there? How many? Yeah, 6. So we have to find each one of them. So it takes a while. I'll just give you what they are. There's one at 0.50, 1.25, 1.57, 1.89, 2.65, and 4.71. And every one of those answers gets a plus 2 pi k. I'm being really sloppy about how I'm writing that, but I think everybody gets the idea. Everyone gets a plus 2 pi k. Any question on how you'd find them? Just do second calc intersect on every one. That's it. Okay, so we really start to get some interesting kinds of graphs. Okay, so here's a summary of how do you figure out what the period is. So if you have sine, cosine, secant, or cosecant to an even power, here's your formula to find the period. It's pi over b. B is always positive. That's why I put absolute value. Tangent and cotangent, it doesn't matter if it's even or odd. This is always the formula you use. The only time you don't use pi over b is if you have sine, cosine, secant, or cosecant to an odd power. Okay, for that, you use 2 pi over b. Okay, so it's the same formula as we've seen before. Pi over b and 2 pi over b. Remember, b is the number that's in front of x. Like, b is 3 in that case. All right, so let's try finding the period of that, just without using the calculator. First thing I do is I say, okay, it's sine to an even power. Okay, sine to an even power. There's my formula. Go back and look at b. Okay, b is 3. The period of this would be pi over 3. Okay, let's say I changed it. Let's change the exponent from a 2 to a 5. Let's make it sine to the 5th. Okay, now I'm going to look at it. I have sine to an odd power. Okay, sine to an odd power. There's my formula, 2 pi over b. In this case, b is 3. That would be the period of sine to the 5th, 3x. Okay, so look at your function, look at your power. That tells you what formula to use. Then look at b and fill b in. And that even works for the basic one. You might think, well, does that work for something like this? Sure. Think of that as, we know the period of this is 2 pi. Think of it as sine to the 1st power. That's sine to an odd. Formula is 2 pi over b. What's the number in front of x here? It's an invisible 1. 2 pi over 1 gives you 2 pi. Okay, so any questions about how to use these two formulas to find the periods? So now there's no more guessing. You don't have to measure stuff on the screen. All right, so we've solved equation. Solving inequalities is pretty much the same thing, except now you're looking at intervals. Maybe we have a graph that does something like this. And it says, where is this function below 0? Where is it less than 0? Well, it'd be an interval. So you still have to do the same thing we did before. Calculate both roots. Now you would just write the answer as an interval. Could be parentheses or bracket, depending on if you include the endpoint. That's also below 0 from there. So you still calculate all your zeros, and then you just write your intervals. If they want below 0, if they want above 0, we can easily do both. Okay, keep in mind we might have vertical asymptotes, so we have to keep that in mind, that you cannot reach a value that's a vertical asymptote, so you'd always use a parenthesis for that. You could have multiple intervals as the answer to a problem. And it's the same approach with intervals. You need to put plus 2 pi k in each part of your interval, because this U shape right here is going to reoccur again 1 period later, and then it's going to occur again. So it's like we have infinite intervals. Okay, but we just add the 2 pi k. Same idea. Okay, so let's try one. I want to find where sine is less than cotangent. Now, it's up to you. You could bring cotangent to the other side and do it like this. Sine x minus cotangent x. And now you're just looking for the roots. Or you could have done it the way I had it originally and looked for intersects. Where is sine below tangent? I'm going to do it this way. Let's type in sine minus cotangent. Get sine. How do I type cotangent in? I don't have a button for cotangent. Yeah. Good. Okay, now I'd have to be careful. If there was something multiplied by this, like 2, I'd have to be very careful with parentheses here. Or I'd change that 1 to a 2. Okay, there's different ways around that. But you don't have to worry about it this time.
If you had the 2 in the first cotangent up top, before you switch it over, would you have to divide by 2 and that's...
No, it would be in the top. You could think of it as this. 2 times cotangent. The 2 would be in the top. Right, because this is cotangent, right? So 2 times cotangent is 2 divided by tangent. That's 2 cotangent. Yeah, keep the 2 in the top, tangent in the bottom. That's a good question. So I think we've got everything we need here. Let's see if we can figure out our period. Sine is 2 pi. Cotangent, what's the period of cotangent? James?
2 pi. Oh, it is.
So it's cotangent to an odd power. You could think of it as just to the first power. So cotangent to an odd power is pi divided by b, and in this case, b is a 1. So what would it be? Just pi. Okay, so the period is 2 pi. And maybe in some problems, that's all they'll ask you for. Find the period. Maybe they won't even have you graph it. Okay, this one they want us to graph. So we've got sine of x. Did I just clear that? That was dumb. Minus 1 over tangent. Go to your window. 0 to 2 pi, all that looks fine. Now we're looking for where it's less than 0. Those 2 curves might look like repeats of each other, but they're not. They are a little different. Okay? So we're not looking at more than one period. I think you can tell they look different. All right, so where are we less than 0? Well, we've got some vertical asymptotes in here. Okay, what I'm going to try to do is figure out, I'm pretty sure I've got an asymptote at 0. Okay, I'm going to type in something very close to 0 and see. At 0.001, I'm at negative 1,000. So if I try 0, I get an error. All right. So from 0 up to, let's see, this point right there, I'm below the x-axis. So we need to find that. Come on, we're in there. So from 0 up to 0.90. And I'm not going to put a bracket because they didn't put an equal to. I'm not using a bracket here because 0 is an asymptote and I can't reach it. Or, now somewhere we're coming back in, okay, down at the bottom, up to this intersection point. I need this asymptote. Well, if I trace, I can probably get an idea. If I see like 3.14, it's probably at pi. Let's see. All right, so all of a sudden at 3.18, I'm at negative. At 3.09, I'm at positive. It's 3.14. Okay, there's an asymptote at pi. You can double check that by trying 3.13 and you get an error. All right, I'm sorry, you get a very high value. Try pi and you get an error. Okay. So we're coming back in at pi. Up to my second intersection point. Uh-oh. All right, so we know we come back in at pi and just grab that other root. Okay, what's tricky, sometimes your cursor goes off the screen for a while and you can't figure out where you are. If you just keep holding it, eventually you'll come back on the screen somewhere. Just hold the button down. Okay, up to 5.37. Now, that interval is going to repeat every period. Okay, so what I'm going to do is just say it's this interval plus, I could shift each one of these numbers by 2 pi k. Could add 2 pi k to that and 2 pi k to that. Same thing here. I could add 2 pi k to each one of these numbers and just take that entire interval and shift it, left or right. So that's how you can do it with an interval. If you want to put plus 2 pi k, plus 2 pi k, plus 2 pi k, plus 2 pi k on each individual number, that's fine too. Okay. That's fine. Any question on that one? All right. This one, I'm just going to graph it. I'm not going to go through all the work. I just want to show you what it looks like. Okay. This time I said just graph it as is. Okay, don't bother moving anything to the other side. So just graph sine 2x and x squared plus 1. So we're probably going to get an interval here. My question is it the kind of interval that is going to keep repeating? Is everything there a periodic term? No, what's on the right-hand side is not periodic. It's a parabola, shifted up 1. Okay? So you're not going to get this shape repeating every period. It's just going to keep going up towards infinity. So let's do zoom 7. See what that looks like. Okay, so there's sine 2x. And x squared plus 1. Let's see, is it just barely? So in that case, actually, there would be no solution. Sine 2x is never above the parabola. It's always below. If you wanted to make it have a solution, we could probably just shift the parabola down a little bit. And I think now we'll have a solution. Let's see. Yeah, now we would. Okay, so you'd be looking for where the blue curve is above the red curve. Okay, so that would be from that intersection point to that point. But that interval would not repeat later on. Everywhere else, the blue curve is always under the parabola. Because remember, that just keeps going up and up forever. So just calculate those two intersection points, and that's your answer. Use brackets this time, because you can't equal. So you use brackets. There's your solution. Okay, just find P1 and P2. I think I'm going to skip over this one. Okay, this one, I'm going to draw it, but we're not going to go through why. It's basically asking you how many solutions this has. Well, let's graph it and just look at it. I want to know how many times it crosses the x-axis. Okay, how many times does it look like it crosses it? We'll zoom in a little bit. It's kind of hard to see.
Now, zoom in.
Well, you can keep zooming in. It's not going to get any better. Okay, what's happening here is it's crossing the axis infinitely many times. Infinite. Okay, so it's kind of a weird equation that has an infinite number of roots. Okay, and the quick reason why is you're trying to find, this is an angle. Trying to find an angle that when you take the sine of it, you get 0. Well, I know that if I take the sine of pi, I get 0. If I take the sine of 0, I get 0. If I take the sine of 2 pi, I get 0. So in other words, every multiple of pi, as long as that is a multiple of pi, I'm going to get a 0. So as long as this is some multiple of pi, it's going to force that to come out to 0. Now, if you solve for x, just flip each side. There's an equation that represents every possible root you could have. 1 over pi is a root. 1 over 2 pi. 1 over 3 pi. 1 over 4 pi. 1 over 5 pi. 1 over 6 pi. Let k be any number you want. 1 over 77 pi. 1 over negative 206 pi. Okay, for every single integer for k, you're going to get a new root. That's kind of why. Right? It's kind of just a weird problem, not quite what you would expect. Okay, this will be our last one. There's 2 here. I think I'm just going to do one of them. It's solving a double inequality. This actually is pretty simple when you have color on the screen because you can see it really well. But the idea is you just graph all 3 parts and then interpret the picture. So I'll graph negative x, positive x, and x sine x. Okay, and let's see what that looks like. So we graph negative x, that's just a line through the origin, slope negative 1. Positive x, line through the origin, slope positive 1. and then x sine x. What the number in front is going to do, that's an amplitude change. But it's a constantly changing amplitude. It's not like I put in 3. Now it's going to just take and triple the height. Well, this is going to change the height, but it's going to change it more and more. As you get close to the origin, it's going to make the height 0. As you get further and further away from the origin, it's going to start to make it bigger and bigger kind of as it goes. Okay, so there's negative x. There's positive x. And oh, did I keep something else in there? What's that?
There's negative x, there's x sine x, and there's something else on the right.
Yeah, there's negative x, x sine x, and positive x. Could be my zoom. Let me fix my zoom. Yeah, it was my zoom. Okay, let me zoom out a little bit. See a little better. Okay, that x sine x, that's that constantly changing height. Okay? So we are looking, let's see. We did that one in blue. We did this one in red. And we did this one in black. So to make it simple, we're looking for where the black one is above the blue and where it's below red. Okay, in fact, if we can, let's get that picture up here. Okay, we're looking for where the black one is above blue. Okay, so over in this area. And we're also looking for where it's above, let's see, below red. Okay, so that would be kind of everything right in here. Where I just shaded, it's above blue, but below red. Okay, so how would you describe where that region is? It's when x is what? Yeah.
Greater than 0.
Yep, greater than, or you know, we can equal. It could be equal to it right there. Yeah. So everywhere x is greater than or equal to 0, you get a solution. And I think we'll stop with that one. Okay, the book does one more. If you have a chance to try that one on your own, you can try it. It ends up being the exact same picture. What's different is the top part is all one piece, and the bottom part is all one piece. So it's the same X shape, but it's formed differently. Okay? All right, so the homework, it's a lot of graphing, so you will need a graphing calculator. And it's 5 through 7, 11 to 15. And then 19 to 25, just the odds. 29, 30, and 31, that's all. And then 33 to 37, just the odds. Okay, so we'll take a look at that tomorrow, and then we'll finish up our last section for the week.